theoreticians and experimentalists with the title Importance of Elastic Scattering in Nucleon-Exotic Nucleus Experiments. You have.
Thank you, and I'd like to thank the organisers for inviting me, particularly Athena. And whenever I am asked to come to Greece to give a talk, I can never say no. Ευχαριστώ πολύ. I gave this talk last year as well at another conference in Greece, particularly because of the increasing interest in looking at hadronic interactions involving exotic nuclei, particularly with regards to transfer reactions or capture reactions. And again, that was emphasized this morning when in the two talks that were discussing double beta decay. So the issue becomes then, how should we approach the issue of describing the interactions between two hadronic systems, one of which would be potentially an exotic nucleus, and then what constraints can we put on them before we delve into applying those interactions to other reactions. So I'll be talking particularly with regards to what has become known as the Melbourne G-folding model. That was actually my PhD quite some time ago. And the other bit, with time permitting, will be on MCAS, the multi-channel algebraic scattering theory, which we developed, my colleagues and I, for low energy scattering involving two hadronic systems. My collaborators, Ken Amos, my partner in crime for quite a number of years now. We've known each other for almost 40 years. My student, now Dr. Kalisa Murulani, as of 3 weeks ago, he was officially conferred, from Johannesburg. Paul Fraser from the University of New South Wales, Luciano Canton, INFN Padova, and most recently Carlos Bertolani, and we need no interactions there. Now, let's put that. Let's say, for example, we're looking at quasi-free scattering with radioactive ion beams between 100 MeV per nucleon to 200 MeV per nucleon. The problem is to define the interactions between the projectile and target at these energies and how to constrain them. And we go back to basics. We look at elastic scattering. And the reason why I say that is because a lot of people in the community think that it is a solved problem, the optical potential is easy, it is anything but. And we need to look at the elastic scattering data because that constrains the underlying optical potential, and especially then the relative wave functions between projectile and target. And that applies to anything beyond elastic scattering. The formal theory of the optical potential gives us the constraints, and this is due to Hermann Feschbach, and he wrote this down 60 years ago. It's important to note that because with regards to understanding what should go into an optical potential, we seem to forget that all of this was done quite some time ago, and we associate the term optical potential with the elastic scattering channel only. And we split the Hilbert space of the scattering solutions from the Schrodinger equation into two subspaces, one involving the operator P, which projects onto the elastic scattering channel, and Q projects onto everything else. So to span the entire space, we then end up with P plus Q equals 1, PQ equals QP equals 0, Q on the ground state of the target equals 0, etc. And leads to the set of coupled equations. When you recouple them, you end up with a Schrodinger equation for the projectile wave function as given here. So that defines effectively a distorted wave, and it depends on this kernel which couples the P space to the Q space. And here becomes an important issue. We define the optical potential as the second of the two terms, and so we have a situation here. It's dependent on this, where V is the underlying nucleon-nucleon potential, and we have this second term which goes into the effects of the Q space. And what is important at this point, and it is often sometimes taken for granted, and the implications are not that well known, it is a many-body problem. There is no exact solution to this. And so from this kernel, and from the fact that we have a target here, what we end up seeing is that the optical potential has to be complex, non-local, target, because it is dependent on the target ground state, and energy dependent. There is an energy dependence that sits there and there. So there are 4 conditions that an optical potential must satisfy. And we have 2 possibilities. At low energy, let's say below 10 MeV, we have coupled channeled methods, formation of states in the compound A+1 nucleus in the elastic scattering. And for that, I'll talk about MCAS, the multi-channel algebraic scattering, towards the later part of the talk. And we actually wrote a book about it, which was published by Springer Nature 5 years ago. At intermediate energy, which is going to be the bulk of the talk today, anywhere between 25 and 300 MeV. At 300 MeV, that's the absolute limit for us, because we end up getting into the particle production channels in the nucleon-nucleon potential itself with the formation of the delta. And so we do not go beyond 300 MeV in terms of this particular theory. And we have folding and end potentials with target structures to form the potentials. And the review article that we wrote on that was in one of the last of the advances in nuclear physics. That's the reference there, published 25 or so years ago. So what do we have? We have a G matrix, and that's what we have. So the effective NN potential is obtained from the G matrices. We use the Bond-B interaction for no other reason than the fact that it was available to us at the time. Remember, this was 30 years ago when this was developed. We use a momentum space effective interaction mapped to coordinate space to use in the DWBA programs of Jacques Reynal to then, from the G matrices and the local density approximation therefrom, to get differential cross-sections and spin observables. But the densities we obtain from credible models of structure, and this is where the nuclear structure becomes central. And the G matrix is a solution of the Bethe-Goldstone equation, which I show there. So there's my bare interaction. We have a Pauli operator, angle averaged. The energy denominator accounts for medium effects, so we can never reach an actual pole there, so we don't have to worry about introducing a complex part there. And it depends on auxiliary potential. So an effective mass can get in there as well. To construct the optical potential from this, which is in infinite matter, we then go to, there we go, in coordinate space, we do a double Bessel transform to get there, and we end up with 2 terms. The first term is local. It's constrained by that delta function, and it is the direct term. The direct term is what is conventionally known as the T row or the G row approximation. And it is not, it is local, as I said. To introduce non-locality, we have to admit exchange terms. We're dealing with like particles here. A nucleon is coming into a system of nucleons. The possibility is that the incoming nucleon will knock out a like particle, proton knocking out another proton, still undergoing elastic scattering, or neutrons as far as that's concerned. And all the non-locality comes from that second term. And here the structure of the target is critical through 2 means. One is through the single particle wave functions, which are in this integrand or in this sum. And the other is in the numbers n, which are the occupation numbers coming from the relevant shell model, because we use the shell model here with regards to that. So the nuclear structure that we have depends on this particular reduced matrix element, the one-body density matrix elements which we get, and they're coming from the shell model. The single particle wave functions are set and consistent with nucleon separation energies. And we classify them as two. One is the harmonic oscillator. We call that the naive shell model, and that gives natural skin attributes. The other we use as Wood-Saxon wave functions in the one body part coming into the cross-section. So this factors out and gives the appropriate extension of the nucleon density consistent with a halo or a skin. So let's test this, and this is where the density dependence comes in to play. I'm going to look at carbon-12 and then on to helium-6 and helium-8. And that is something that Athena and I worked on quite some time ago in a very nice paper. So we assume that the projectile and target are both hadronic and the interaction is encoded in the potential, and we have to look at constraining that potential or testing that potential in our case through elastic scattering and through the analysis of both the differential cross-section and analyzing power. So let's see what we have. This is carbon-12 at 200 MeV, elastic proton scattering. And you see on the left is the T matrix and then the G matrix. So this is, as a T matrix, the T-row approximation, that's the free space situation because the T matrices are defined for free space. And if you compare the two cross-sections, the predictions that come, there's no fitting of the data here. There's not a lot that can differentiate between the G matrix and the T matrix. That's an important result. But if you then look at the spin observable, if you look at the analyzing power, you can see that the density dependence is quite stark. And the G matrix gives the analyzing power at 200 MeV as opposed to the T matrix. And a lot of people, when they were doing the calculations, this goes back to the time of Kerman, McManus and Thaler in the 50s, they look at that and they say, aha, the spin is not being described well. It must be a relativistic effect. So all of the motivation for doing relativistic optical potentials, even as low as 60 MeV, is due to the fact that in the free space situation, they could not describe the analyzing power. If they moved then to the G matrix with an appropriate model of structure, and in our case, we used a 2H per omega shell model, naive one of the first no-core models back in the early 90s. This, in both cases, all of these calculations are predictions. The red and the blue is simply a case of using either harmonic oscillators appropriate for mass 12 or the appropriate Wood-Saxon wave functions for carbon-12, and they give the same result as one would expect. If we go to helium-6 and helium-8, and I'm referring in this case to an article that Ken Amos and I wrote in, published 11 years ago, the data coming from Sakaguchi, we have for helium-6 at 71 MeV per nucleon, and we have two results. That's been well known, the cross-section. What was new to us was the analyzing power that was done in that paper, an incredibly difficult experiment to do. As you can see, to get some semblance of statistics, the data were binned at 10-degree intervals and still had large errors associated with that. But what is clear from there is that the analyzing power has very little in it and is close to zero in both cases. And again, this is a prediction. There's one additional point to be made at this, but I won't make it just yet. If I look at helium-8, I see the same situation. And again, predictions in both cases for the cross-section and the analyzing power, and you can see we're getting quite good results despite the fact that the experiments are difficult and it is still a prediction. The energy dependence, here we have two sets of data. One comes from Ganil, and that's the experiment that Athena and collaborators, Nicholas Alamanos group at Saclay had done, and we were approached to do the theory. The other was from Dubna, the Ganil experiment at 41 MeV per nucleon, the Dubner experiment at 25 or 26 MeV per nucleon, and now you see the actual energy dependence coming into play. You don't see it against scattering angle. You have to make the transformation to momentum transfer to do that, and this is what we did here. But I keep saying, this is all prediction. When did we predict this? Not the lower energy ones, but this is at 71 MeV per nucleon. That came from this particular paper, which we published in 2000, 13 years before those analyzing power data became available. And this had done so. So we didn't have to do a single thing. We just pulled up the old data files, the results, and see if we got any agreement. And to our bewilderment, we did. And it was quite a good surprise. But it's showing the fact that if we wanted to do some constraint on the cross-section, not only do we need the cross-section, on the optical potential, not only do we need the cross-section, but we also need this, at least one spin observable. The analyzing power being difficult to do, I'm hoping that the mantle can be taken up. Let me go quickly with regards to low energy scattering. MCAS, we want to get S matrices and evaluate the total elastic scattering cross-sections and the total reaction cross-sections, which we get from the appropriate elements of the S matrix accordingly. The MCAS approach is built on finite rank separable representations. We get the matrices, the S matrices, from those Schrödinger, and we use Sturmian expansions to define the form factors that come into play. And we solve the Lippmann-Schwinger equations accordingly. And we use a collective model, which has a particular problem. We solve these in momentum space. And in so doing, what we can find are, in fact, the sub-threshold states, the bound states of the compound nucleus, which are not accessible by experiment. And when we look at this through the collective model, and do a naive collective model of the projectile coming in and coupling to the nucleus, there is no restriction on where that incoming nucleon is going to couple to within the nucleus. And so the Palli principle is violated. And when we see that violation, and we look at the states in either nitrogen-13 or carbon-13, we see a hell of a lot more states coming into play than actually exist below threshold. There's only one state below threshold in nitrogen-13, that's it there. And there are only a couple in the case of carbon-13. And what we do is we add orthogonalizing pseudopotentials, which effectively block those particular states, those spurious states, which are unphysical. And when we do that, not only do we get the cross-section, this is for neutrons on carbon-12 to give us the resonances in carbon-13 and the background, again, a prediction, but also the spectrum from the carbon-13 ground state all the way up to about 10 MeV. So to conclude, we have optical potentials at low and intermediate energies. They're complex, non-local, target, and energy dependent. And we need such potentials as necessary to obtain the relative wave functions of the projectile and target, and elastic scattering is essential to constrain the optical potentials used. And this is important with regards to what was mentioned this morning with regards to the double beta decay. When you have the sequential channels, as I was seeing this morning, to go from, say, the selenium-76 to the germanium-76 and go into the intermediate steps, you need then, if we're going to keep to these criteria, as Feshbach told us to 60 years ago, we would have to calculate the optical potential at each step. That's where the difficulty comes in. That's it. Thank you.
This paper is now open to questions. Do we have something? Okay, perfect. I was speaking Karataglidis, but okay.
Yes. So thank you very much for the very clear, let's say, talk and this basic information on elastic scattering. So as regards the last point, I mean, we take this into account. You enter with the dual, and there is a lot of cancellation, but not complete cancellation.
No, there isn't. No.
Yeah, but that's we account for that, and because it's an important term. And I have a question. You mentioned the fact that below 10 MeV bombarding energy per nucleon, you have a regime between 30 and 200 MeV.
Mm-hmm.
It is good.
What's missing?
Yeah, but from 10 to 30.
That's what I tend to overlook. We enter into the realm of giant resonances, and that becomes the most difficult problem with regards to the optical potential. Mm-hmm. And our formalisms do not take that into account. Very few papers have actually tried to describe the giant resonance region microscopically. Mm-hmm. Ken Amos and Heinz von Geram did so in 1975. When we moved to the low energy regime, we were going to try and do something with the giant resonances, but there was no interest. We went straight to the low. So
but maybe there is a recent paper from Angela Bonacorso and Bob Charity that they were doing just this.
I have to look at what Angela's been doing lately. I haven't kept up with that regard, so I'll follow that up. If she's done anything interesting in the giant resonance region that I can then apply, then that might be useful, yes.
I have just a curiosity. At the beginning of your talk, you said that the one-body transition density are calculated within the shell model framework.
Yes.
But do you mean the interacting shell model or just the mean field? Because you mentioned...
Just the mean field, just as a bulk standard
just
shell
the
model.
mean field,
Because we're only interested in that regard from the specification of the optical potential in obtaining the transition density matrix elements, as defined by that reduced matrix element that I showed. Whether it's the which reduced to the occupation numbers in the case of elastic scattering, or a transition matrix element for inelastic scattering. And that works very well to this day. There's no exotic features that need to be introduced of anything in nature. For helium-6 and helium-8, we were using a 4H barometer shell model based on the Zheng G-matrix interactions. And that worked.
Clearly, you cannot do this kind of work with interacting shell model. You cannot include all these kind of orbitals, of shells.
That's where the problem comes in, because you effectively have to map it to some sort of one-body reaction or scattering matrix element, which requires the use of the single particle wave functions. And you have to map onto some sort of basis, which is finite dimension. And there you need to know which orbitals you're considering.
Thanks.
Okay. Thank you, Steve. We move to Professor Chengjian Lin from the China Institute of Atomic Energy. He's going to talk to us about reactions. He's going to talk to us about reactions of weakly bound nuclei at near barrier energies. We move now from much higher energies to very low energies, and we can see perhaps the changes in the optical potential.
Okay, thank you very much. Good afternoon, everyone. It's my first time to visit Greece, so many things to organize and particularly Argentina for inviting me here to attend this wonderful, excellent workshop. Okay. Our group is experiment reaction, nuclear reaction group in CIA, but we also did some. We did many things. This topic is only one of our group. So today I would like to review this work in our recently work in the past years on the reaction of weakly bound nuclei near barrier energies. And, this is the contents of my talk. Actually, it's included two topics first is on the optical potential, optical model potentials of the weakly bound nuclei, and second is the breakup mechanism of the weakly bound nuclei. And I would give some examples for these two topics. Okay, let's start the first one on the optical model potentials. I think all of you. Sorry, where's the point? Oh, sorry. Yeah. I think all of you may know the optical model potentials really well, even better than me. And in this model, the potential consists of two parts. One is the real part, and another one is the imaginary part. And when it's introduced to the nuclear physics in 1949, it's not dependent on the energy. And up to 1984, 85, some experiment find the imaginary part. As you see here, this is for the oxygen system on lead-208 system. And of course, the energy above the barrier, way above the barrier, is almost constant for the imaginary part. But when you approach to the Coulomb barrier here, and we can see in the imaginary part, imaginary potential is quickly decrease and then go to the zero. There's a threshold appeared, and meanwhile there's another bear-like shape appeared in the real potential. This is anomaly. So this phenomenon is so-called threshold anomaly. This is universal phenomena in when the energy near the Coulomb barrier. Now, as you see here, the potential now is related to the energy. It's dependent on the energy, and this real part is can be separated to two components. One is the almost constant, and this is come from the space non-locality. And another one we call it is dynamic polarization potential. Sorry. And this one delta V is can calculated by the imaginary part. And this formula is just the dispersion relation is result from the causality principle. So, and okay, as you see here, this dispersion relation can reproduce the experiment data is rather well. And also we found many things have such kind of threshold anomaly. But remember that this is only for the tightly bound nuclei system. For weakly bound, the situation is different. Yeah, as I show here, this is for Lison 7, Lison 6. Both these nuclei are weakly bound. But as you see here, for Lison 7, it's almost okay, almost normal threshold anomaly. But for this one, we see the imaginary part is increased even below the barrier. And of course, the data is not so good here. We don't know it's increase or decrease. It seems decrease here. And the important question is still the dispersion relation still keep for such kind of system or not. And also, this is the universe phenomenon for the weakly bound nuclei system. So we call it abnormal threshold anomaly. And how about the halo nuclei? As I showed here, this is for the helium 6, yes. And there's elastic scattering angular distribution. We can extract the optical potential from this data and showed here. Again, we see the imaginary part is increased, but we don't know where is the threshold and how it's affecting the real part of potential. So from the experiment point of view, I think it is most important to determine where is the threshold energy for such kind of weakly bound nuclear system. But it's quite difficult because below the barrier, as you see, the angular distribution of the elastic scattering becomes flat. It means it's quite difficult to get a nuclear potential from such kind. All of this is Coulomb scattering. So it's quite difficult to get some information on the nuclear potential. So we propose another method is called the transfer method. Because as long as the transfer occurs, the nuclear force should have some effect. So it doesn't matter the cross section is high or low, as long as it's present. We can get some information on nuclear force. So after the idea is quite simple, as you see here. This is just a standard DWBA equation for such kind transfer reaction. And in such kind calculation, we have 4 wave functions, 2 for the bound state and 2 for the scattering state, incoming and outgoing. And for these 2 bound states, we can calculate simply by using the single particle potential model. And then we can calculate the overlap of together this one. This one we can measure in experiment. Also, this one we can measure. So after that, we can determine this one to get the potential of the outgoing channels. So by this method, using this method, we measure the several systems as I list here. And in the following, I just mentioned this one because this is the outgoing channel is helium-6 on the bismuth 209. This experiment we performed 2 times. The first time is in 2004, mainly on the energy near and above the barrier. And after more than 12 years, we performed another experiment, mainly on the barrier, below the barrier. And this is in the barrier energy. And we use in the raising the silicon strip detector for this purpose. And we get a delta E particle identification. As you see here, this is in the Listen 7, and helium-6 is over there. And from the projection, we can see a lot of state here. All these states are single particle state in bismuth 209, yes. And X factor is already determined by other experiment. And I just simply show you how to analyze this data. This is in the incoming channels. We can feed to get the incoming channels potential, and then feed the transferred angular distribution for different energy, then to get the potential of the outgoing system. Okay, the final result is just right here. This is the imagining part, and we see the increase and then decrease. There's a threshold here, as you see. It's well below the barrier, about only 0.7 below the barrier. And the important thing is, this is our data, and important thing is this one. This curve is calculated according to the dispersion relation. As you see here, it's not an agreement with our result. So from this data, we think the dispersion relation cannot describe such kind of weakly bound nuclear system. And this is only one system. Another system is Listen 6 on lead to oil. It's already studied, but but energy is not so low, not well below the barrier. So recently we decided to using the same method. Of course, we can measure this directly to the very low energy, and also we apply the transfer method to get optical potential at very low energy. And I just quickly show you some results. And this is for listen 7, listen 6, listen 7, for the angular distribution for several energies, which high precise data. And then this is the transfer reactions. And with this data, we can get the potential. This one is for listen 7 on that 208. And it's quite similar to the previous results. This one is showing a normal threshold anomaly, but for these two, and this is directly extracted from the elastic scattering, and this is from the transfer reactions. As you see, these two is quite similar for these two methods. Results, I mean, increase and decrease. There's a threshold here. And of course, this is a preliminary results, and in the future, I think we should combine these two data in the same way to get only one result. So now I think there's some. I would like to discuss some point on this dispersion relation, because you know. Any particle or wave pass through a media should obey the dispersion relation. But now at least these two systems we see it's not applicable, the dispersion relation. Of course, there are some reasons. I think I have no time to explain them in detail, but here I would like to point out one interesting thing is this one, the negative index of the reflection. This figure is just I showed before, and red one is the normal dispersion relation predicate, but if you inverse the index of the diffraction from the positive to negative, then you can see in this one, the dash line, the green dash line here. And this is in good agreement with the experiment data. So it's quite strange to me. I think maybe such kind of exotic nuclei, maybe next is a metamaterial, something like that. This is a very hot topic now in the materials science. So this is one possible reason. Okay, I think maybe I have no enough time to complete. Sorry. yeah. And okay, I quickly pass through the slides. And for the weakly bound nuclei reaction, I think the most important issue is the breakup. So the mechanism of the breakup is the main purpose we would like to study it. And this figure just shows this is for boron 8 on anyway 120. And then boron 8 we know is a candidate for the proton halo nuclide, and one proton, of course, is inside the potential where, but it's quite close to the continued environment. So at this time we may name it as semi-open quantum system. Is now fully opened. After during the collision, it really is excited to the continuous state, and then it's a true open quantum system. And of course, in the theory, we can use in the CDCC method to calculate such kind of process. And in an experiment, I think it's quite difficult to identify the breakup or transfer reactions. As you see here, this is the typical transfer reactions, and this one is breakup and followed fusion, incomplete fusion, and as you see in the product is exactly the same. But fortunately, we know this is three-body kinematics, and this is two-body kinematics. So I think that we can use the complete kinematics to identify the different reaction process. And then this is just our interest in the nuclei, stable and unstable here. Okay, and then we did a lot of experiment for radioactive beings, mainly based on two facilities. One is the River 1 facility, and another one is the Sea River facility. This is in China, this one is in Japan. And we also built a lot of detector arrays to do the complete kinematic measurement. Okay, I just quickly pass through the results. This is for Listen 6, 7, and we have a good particle identification and also the correlation between two fragments, and we can see a lot of, this is just Q value, and we can see a lot of different decayed mode. As you see here, this is alpha triton and alpha proton, something like that. And also we have the relative energy between these two fragments, and also the angular correlation. This is the angular correlation, and I have no time to explain that. And as you see in this line, just the resonance state. Different time scale have a different influence on the reaction process. And this is just preliminary results for the different branch ratio of different decay mode, decayed components. And some of these data are already published, but not all the data, because we hope we need a uniform theoretic to describe all this data. Okay, I have no time to have. Okay, this is another system on fluorine 17 on lead 208, and this is boron 8 on tin 120. And I think I just quickly show the conclusion here for fluorine 17. The conclusion is the non-elastic blackup is dominant, but for boron 8, the elastic blackup is dominant. So it's quite different from these two nuclei. Okay, that's all. Thank you very much.
To discuss a lot about the optical potential at near barrier energies, as well as the breakup. Very interesting results of 8 boron, and because they are coincidence results very seldom we can obtain. Yes. So you put a lot of questions, yes, but we can discuss it. Yes, and we have several comments to do. Now this paper is open to questions for all the audience. Yes.
Please.
Okay, thank you very much for for making this very nice review of this kind of topic. And it makes me to remind the work we have done in this subject for quite a while. Just like to draw your attention to the fact that there's a set of publications exactly on the same reaction, exactly in the same energy range, which were studied with 4-pi detector, in which proton alphas and so on were measured. And these work are from Cosimo Signorini, Marco Mazzocco is one of the next speakers, and me, and myself. Okay, and okay, no, it would be interesting to see if this set of data that be spanning about 10 years of work on this kind of will overlap with yours, because we do exactly the same work with the, with the anomalies and so on. So it would be very nice to see. Now I don't remember my data. No, but I wonder if he try to, because in example we extend the Cayley data to larger energy range and so on. And so it would be nice to see this data overlap to your data, to see if there are similarities on the result.
There are some contradictions also with our data.
Okay, so.
I said a lot lot of comments.
Okay, so it will be discussed tomorrow. So I'm happy because
Yeah, I think
nothing of this was mentioned, but okay, very good. Okay,
Yeah,
so
yeah.
you answer for him.
Yeah, sorry that I have no enough time to explain clearly. Yeah,
Until
yeah, yeah.
okay.
So you produce in China this helium-6 at low energies
Yes, yes.
and boron-8?
Yes.
But the
No, this is, we perform this experiment at CNS, the C-Lab.
Oh, sorry.
Yeah, yeah.
Okay. But okay,
Yeah.
thank you.
Okay, Francesco, and then Marco.
No, it's about the dispersion relation that you mentioned.
Yeah, thank you.
Okay, in principle, you should integrate from 0 to infinite in the end.
Yes,
Yeah, and
yes.
I don't think you did that. So is there any cutoff of some, because, I mean, it's a nice relation.
Yes,
but
yes.
Then you cannot apply simply. Very easy.
Yes, I think there's two methods. First, you mentioned one of these, integrate from somewhere to the infinity.
Yeah.
Yeah. So of course there's some cut it because in the part it's no meaning for us. I think. In our case, we just determine the sensitive. Sorry here. The sensitive radius. This can be determined by I think there's a so-called I don't remember the name. Notched. There's a notched method to determine this one sensitive radius. Then we compare this potential and this it's not integrated, the volume integrated. This is just a sensitive radius. Okay.
Okay. This method. Okay. But anyway.
Yeah.
We were talking with Steve Karataglidis
Yeah.
yesterday, who's not now here, that because it is so difficult to obtain the optical potential at near barrier and below barrier energies, and the data sometimes perhaps they are not what they should be. So at least two measurements
Yeah.
have to exist in order to take out a result.
Yeah.
Apart of that, because Chengjian started to discuss about another observable, which is the
Yeah.
transfer, which even that is not enough. And we have a couple of papers, and we discussed that subject, that at least total reaction and fusion, they are very important if we want to extract the energy dependence of the potential,
Yeah.
and to find out if the dispersion relation holds or not.
Mm-hmm.
And for that reason, tomorrow we have to discuss it.
Okay. Yeah.
Okay, very briefly, congratulations on the beautiful data and beautiful analysis. Could you show?
We have not seen when the boron made data, coincidence data.
You are one of the authors.
Yeah. I'm aware, but I was not aware of the data lithium 6 and 7 on bismuth 209. Can you put again the slide that I can just write what is the publication?
This one or
No.
which one?
No, lithium 6 and 7.
Oh, this. Oh,
This
sorry.
one.
This one on bismuth.
No,
Huh? Sorry. This one?
no, go on. After the threshold anomaly, okay.
Oh, after that.
Slowly. Here.
Ah,
Yeah.
yeah,
Okay.
yeah. No question?
We thank again.
Okay, thank you.
From Padova University, Marco Mazzocco, will speak to us about the upgrade of the root facility exotic as LNS.
Okay. So thank you very much for the introduction, and welcome back. Yeah? How are you? I must say that I've never been so relaxed before giving a talk, because I know the hardest part has already gone. Yeah? And so friends are also allowed to ask questions this time, yeah? Because, okay, and this is also for me my first presentation after nearly 5 years because of the pandemic and also the aftermath. I didn't have too much, just little chance to travel, so it's a way somehow to restart, and I accepted the very kind invitation of Athena and the organizer. So it's a way for me somehow to be back to business. And also because my work in the last year has been mainly technological, I mean for the upgrade of the facility, but we will have time somehow to discuss about opportunities in the coming weeks and coming months. So our facility in Legnaro is devoted for the in-flight production of radioactive ion beams. For those of you that are not very familiar, we used the in-flight technique, so with heavy ion beams from our tandem accelerator on a gas target. The commissioning occurred 20 years ago. We had a substantial upgrade process in 2012, and so far we deliver 8 radioactive ion beams. This is a picture of the facility. So the beam comes from the left, and then here is the location of the gas target, and over the years we also have in operation a cryogenic gas target. Then primary and secondary beam, they travel together through the first quadruple triplet before the first selection stage with a 30-degree dipole magnet. And then we have a second selection stage with a 1 meter long Wien filter, so with selection in velocity. And then the second quadruple triplet, and here is the place where we use to perform experiments. For us, it has always been much easier to go to the proton-rich side of the nuclei chart, just 1 or maximum 2 mass units far from stability, and in many cases with good intensity, 10 to the 5 for beryllium-7, even 10 to the 6 particles per second, boron-8 and carbon-10, maybe 10 to the 3 particles per second, and neon-18 was just under development when we had to stop our activity. Somehow you will see the reason why. Concerning the main topics that we investigated, essentially reaction dynamics at Coulomb barrier energies, and this was the origin of the collaboration with Athena a long time ago. We also performed 2 resonance scattering experiments in collaboration with the University of Birmingham, and also 1 experiment of astrophysical interest, again with the Trojan horse method. So what happened a few years ago? So the Agatha gamma spectrometer moved from Ganil to Legnaro, and actually we immediately realized that for the installation of the setup, and especially the platform with all the services, our scattering chambers at the end of the beamline were not compatible with the installation of the spectrometer. However, so we had to remove them in 2021. However, we realized what was somehow the original idea, so that was to couple our beamline with Prisma. So that was the magnetic spectrometer Prisma. So that was the idea why the original layout was in the same experimental hall with Prisma. However, somehow the conjunction of the 2 equipment has never been somehow achieved. Now we realize it's somehow the focal plane of Agatha is just 2.68 meters downstream of the standard focal plane of exotic, so we made some ion optical calculations, and we realized that the existing equipment would be enough also to focus the beam downstream. However, we expect to have a sort of 50% reduction in intensity, and also I'm a little bit concerned about what is going to be the beam spot on target, so we will have somehow to think about, carefully to think about the collimation, also because at this time, Agatha is going to be very sensitive on the way that we collimate and we stop the secondary beam with, so this is still somehow on the way. In the meanwhile, since we had to stop when the somehow experimental world was accessible, because now I would say 90% of the beam time is dedicated to experiments with Agatha, and most of Europe and even from North America are coming to Legnaro for experiments. So we decided to take the chance to upgrade our facility after 20 years of operation. So we changed power line, signals, cable, beam. Also, then we allocated chamber for beam diagnostic, vacuum control, gas target control, the insulation of the pipelines for the liquid nitrogen, the water collector. So you can see that now there is almost nothing on ground. And we also have these way here for all the cables, and also the remote control, which was, 20 years old, so now it's on a new platform based on the EPIX software. So everything is almost, I can't say brand new, but at least renovated. And we performed the first commissioning run at the end of October last year. As you can see, we installed the same chamber as before, but now it's suspended, just to allow Agatha to rotate. And in this case, so it was the first experimental run after nearly 4 years of inactivity. So we restarted with the easiest beam that we produce, so beryllium-7 4+, and we quickly checked somehow the reoptimization of the primary beam focusing procedure. We got and reproduced the same conditions that we had 10 years before, the last time that we ran with beryllium-7 at such a high energy. So the tuning of all the optical elements of the beamline, now they work with the new software, which was ready and debugged, I would say, the day before we started the run, but this is somehow a usual situation, somehow that you manage to fix everything right before the experiment. And also we tested the capabilities and the performances of Agatha under the Newton flux, which is originated by the fact that the secondary beam is produced with the PN reaction. And here you can see the tuning of all the ion optical elements in order to, and here you can appreciate what was the original spectrum when we start the optimization with mostly the scatter beam lithium-7, and then at the very end we manage somehow to get again a beryllium-7 beam, practically 99% pure. In the meanwhile, we also decided to change our tracking system, event-by-event tracking system. In former time, we were using PPACs, so gas detectors in the multiplication region. We went for MCP. It was a little bit of an adventure to provide and to somehow to buy the microchannel plates, because the production was mostly in Russia. And also, German companies and also Japanese companies, they were somehow obtaining the microchannel plate from some Russian companies. So at the very end, we managed to buy 2 detectors from a German company, this Rontec. On the carton box is still written Amamatsu. They were delivered at the end of July 2023, so it's a little bit suspicious, but anyhow. Instead of a rectangular shape, we had to go for a circular shape of 104 millimeters. But the layout of the mechanical support and also the electronics is based on the microchannel plate, which is the starting detector of Prisma, in order to be somehow to have everything later on compatible with the other. And we designed all the pieces in our mechanical workshop. We assembled it for the very first time. This was in November last year. We also learned how to do the delay lines by ourselves, because we asked a German company, and somehow the cost was something like 10,000 euros per delay line. So we thought together with Rosanna De Palo from University of Milano, she was a former postdoc of Prisma, and she's Sara, our postdoc in our group, that maybe we can also start somehow a business with these delay lines. The readout electronics also is new from our workshop in Padova, and also we have to study a little bit how to make all the connections. So finally, we were ready to test the detector, so the second commissioning run. This time, we were ready 2 days before the experiment, but we had a vacuum problem with some feed truth that cost us 1 day. So essentially, we turned it on just the day before the commissioning run, and we realized that, everything was ready because we have the beam time, but then we had somehow to work in the laboratory to test all the equipment and to check carefully all the electronic chain for at least 2 months at the beginning of this year. So this was the first test with the alpha particles without the carbon foil. And this is the first spectrum that we obtained in laboratory, so rather good. Here there is a written exotic, and I challenge you to see that in some sense it's also here, EXOTINC, so it works. The following step was to put the mylar foil illuminated, and then we tested the time of flight resolution, better than 600 picoseconds, and also the position resolution, which is actually we tested without magnetic fields in order to avoid the dispersion of the electrons. And since there was some strips in front of a kind of crooks in front of the detector. We thought it was this one. When we put the magnetic field, we realized where it was actually the position. So the position resolution is of the order of 2 millimeters. Then we developed also the tracking algorithm, because the idea is to have an event by event on-land tracking of the particles at the target position later on for the experiments. And in this case, we used what we now call EXIDE, is one of the last examples of the former EXPADES detector, because we had a spare one with a thickness of 1 millimeter, 64 times 64 millimeters, delivered by Micron, 32 times 32 strips. So we put it essentially, so here is the alpha source is here, the microchannel plate, and the detector was put essentially at 0 degrees in order to have at the same time the alpha particles passing through the foil, releasing a signal on the microchannel plate, and then in order to have a gate on the DSST and also to be sensitive on the position. Also in this case, we put some strips in front of the detectors in order to check the resolution, and now you can clearly see. And here is the gate on the silicon detector. Just to have an idea, we have a sort of somehow reflection of the events in the central part of the microchannel plate. If you flip it, you can somehow see everything from the perspective of the alpha particles, and later on it will be the beam. And concerning the tracking algorithm, using the position, the microchannel plate, which is tilted by 45 degrees, and with the solid state detectors, then we are able somehow to reconstruct the source position. Of course, at the moment, here we just have some points, actually, just for graphical purposes. Otherwise, we can simply draw some lines, but it was a little bit consuming for the CPU. And here is the source position. Of course, we can still work on it, but at least we developed the tracking algorithm. So what is coming next? So the next commissioning runs, you can see from here, we will install a second chamber with the second microchannel plate, and the agreement with the Agata collaboration is that we will remove it just after our experiments. And we will test somehow with the beam passing through the first one, the second one, and we will put our EXIDE at the very end. And this will take place at the beginning of July, so the in-beam test of the two microchannel plates and the tracking algorithm. And then we foreseen at the moment a fourth commissioning run connecting the entire beam line, and the size of the connection is still a question mark, because we need some preliminary information of the beam point and the projection on target. And in principle, there will be a PAC meeting in Legnaro. The coming one will be in July, which is obviously too early. But in case everything is successful, it will be open for experiments to be run with Exotic and Agata for the first semester of 2025. So there is this unique chance to use our secondary beams together with a state-of-the-art gamma detectors located in Legnaro in the present configurations. So I don't know if you are very familiar with Agata, so I got some slides from the Agata collaboration. It's a tracking detector, and in the final configuration we will have a 4-pi geometry, a 4-pi coverage. At the moment, what is available in Legnaro are 12 tripole clusters. The maximum counting rate is going to be 50 kilohertz each. And then you can have two different configurations, or you can vary from a nominal configuration with a distance of 23.5 centimeters, or you can move to the close-up configuration, putting somehow the array a little bit closer. And the basic concept of this detector, and somehow is the European counterpart of Greta in the US, is the fact that the electrode of the germanium is segmented into 36 parts. And of course, you can reconstruct the interaction point. And so in this case, you do not need an anti-Compton shielding, and you can, in principle, identify inside the crystals the interaction points. And of course, they have a proper algorithm in order to recover somehow the efficiency of the setup. This is the timeline of Agata. So everything started in 2010 at the demonstrator phase in Legnaro, and we even had a nice stamp out of the original campaign, and it moved for 2 years to GSI, for 6 years to Ganil in France, and then it moved in 2021, commissioning 2022 in Legnaro. It will stay up to 2026, probably with an extension of 1 or 2 years. The physics coordinator is Magda Zielinska from Saclay, and the local coordinator of the project manager in Legnaro is José Javier Valiente Dobon. There are actually 2 possible configurations of Agata. The current one, which is coupled to the Prisma magnetic spectrometer, and so this is the beam line taking the beam to Prisma, and our beam line is just 10 degrees aside the Prisma beam line. So we will access from this line here, and it will be moved at some point to the so-called 0-degree configuration, where the NEDA detector array for neutrons will be installed. In this configuration, our beams are not compatible with Agata. So it's not clear at the moment. We also have a new director in Legnaro when the movement will be done. It will cost roughly 6 months. And there is also the option to somehow move to one to the other configuration, and then to move it back after to have a sort of a negotiation with the Agata Council, because in Legnaro, probably, maybe at the end of this year or next year, we might also have uranium beams, and it will be nice to have somehow Agata in the place where it can accept the uranium beams, and the original and the best configuration is the one of Prisma. So we are still discussing. However, first semester of next year, still Agata Prisma configuration and only tandem beams, which for us somehow is the ideal configuration to have a sort of campaign. This is the reference in case you are interested in details about Agata. This is the efficiency of Agata, and essentially, depending on the position, one can move from the nominal one to the close-up configuration at 1 MeV, between 8 to 10%. This is simulation with 15 tripole clusters, and now there are 12, and also maybe take into account instead of 8% in the nominal case, maybe around 6% with respect to the simulation. And what is might be useful for tomorrow's discussion is the set of ancillary detectors, because one problem is that the scattering chamber is extremely small. So we cannot go there and bringing our equipment as we are used, for instance, to run experiment with Luis, Angel, almost everywhere in the world. So we have to use what is available. In the Prisma Agata configuration, so we can make use essentially of Euclides, Dante, Oscar, perhaps Sauron, Spider, the plunger, if we might be interested in lifetime measurement within a certain ranges, or some lanthanum bromide. In the other configuration, which is not somehow relevant for our case, but just for advertisement, Paris, Ctadir, Sugar, Neda, and Grit. So I was selecting, since most of us are essentially addicted to charged particle spectroscopy, the main characteristics of 4 of these arrays. So Spider, and so we have 7 of these sectors you cannot really see in a cone shape, and this is mostly used for Coulomb excitation experiments. The second option is Trace. There are 5 units. This is the one with the highest resolution, so the highest pixelation. And this is a delta E stage, where in case of Spider, it's just a single layer with a thickness of 300 micrometers. In this case, I think up to 5 units can be fitted inside the Agata chamber, and the delta E is 100 micrometers, and the E stage 1.5 millimeters. And here some other details and also the publication. Other option is the oldest one, Euclides, that was in use already at the time of GASP. This is the one that is ensuring the largest solid angle coverage. Of course, at the price, okay, we need also the picture here. Of course, at the price of I would say low position resolution, because these are standard detectors. Only one of them, I guess, it's segmented in one side. Delta E, and okay, in the usual setup, so with stable beams, there is an absorber at forward angles in order to suppress the elastic scattering. I guess that with the intensity of our secondary beams, this absorber should not be necessary. And okay, there are different, how to say, efficiencies for, let's say, protons and alpha particles. I guess it's related to this absorber. In principle, it can also be used in the plunger configuration, but you will use only half of Euclides. And then finally, Sauron. This is, okay, also the picture, because I can see it from here, but you cannot see actually. In this case, these are two annular detectors, single stage. These are DSSD with sector and arches. And the position can be slightly adjusted in order to cover different ranges at forward and backward angles from micron. If we want to do somehow work and we want to detect evaporation, let's say alpha or protons from fusion evaporation reactions, this is somehow the detector that might be used. So I will come to the summary. So our facility, after nearly 4 years of inactivity, has been upgraded and ready somehow to work. We have been developing an event-by-event tracking system based on microchannel plate detectors. Last commissioning runs will be between summer and early fall this year. And we expect to be able to accept proposals and to run a sort of a campaign, 2, 3, 4 experiments, maybe in the first semester of next year. This is the entire collaboration, actually the ASFIN collaboration and the Gamma collaboration, somehow all together. The postdocs that are mostly working on this project, and then as a senior guy at this point of our career, myself and Jose Javier Valiente Dobon. Thank you very much for your attention.
So we will have a lot to discuss tomorrow about
Hopefully,
the
yeah.
possibilities, yes, yes. A lot of things.
I have a couple of questions.
Yeah.
The first question is technical. Yeah, the first is technical. Okay, so you are going to use MCP, so we have a lot of experience with MCP also with Athena. So what about the efficiency?
Yeah, I just forgot to mention. Yeah,
yeah, because you know that we are going to get trouble, specifically if you are going to use two in line. So yeah.
Okay, at the moment with alpha particles, it's 43%.
40, yeah.
Yeah.
You know
with
that you
alpha
can use
particles.
lithium fluoride or some other.
Yeah, because you know a person that you might know very well, Pier
Yes.
Paolo Figuera,
Yes.
and also some other people in the audience.
Yeah.
So we are in close contact with him. He's part
That's
of the
nice.
collaboration and he's coming quite frequently.
So because
to
also you need very
Legnaro.
large, I mean, surface. I
Yeah,
think.
it's
But
100
we have a
millimeters.
technology at LNS. So
Yeah,
that's nice.
and so we took the Mylar.
So you have
illuminated
the receipt.
we made already
You have the receipt, yes.
yeah, the evaporation, and we have different thicknesses,
Yeah, that's
10 and
crucial.
15. Yeah.
Yeah, that's point. So the other is a little bit political. What's, I mean, there is some mismatch or some overlap with space.
Okay, actually we are complementary. In the
That's
sense
political.
that
Yeah, that's a political
answer. No, in the sense that our beams are very light
Yeah.
compared to the beams that you can get with space. Actually, we can overlap with beryllium-7
The beryllium-7 for
because
sure.
it can be produced in a batch mode, but
Yeah.
I think it's not the first one on the list.
Yeah.
Because the first one should be, I guess, aluminum-26.
Okay,
on
that's
the
nice.
list, but
That's nice.
still, I don't think there will be space beams before the end of 2027.
Yeah, yeah.
So
Depends.
to answer,
I know that you are starting now. I think just now.
in principle, yes, but in the meanwhile, we got and we should get the uranium beam.
Yes.
yeah?
Okay.
But yeah, okay. The
Okay,
answer
thank you
will
so
be
much, Mark.
yeah. We will have all the conference dinner.
Yes.
I mean, to
Okay, Luis.
Luis.
Well, congrats for this big job to you and to all your postdocs, students, or whatever, all the people in the it's a very good thing to have again an exotic beam in Italy, because well, we have this during years, and we got very good measurements, and we get fun also.
Yeah.
So my question is, you have an idea of what kind of experiment you are planning to make with Agatha, because it's a very powerful tool now, because you have Agatha plus NEDA, and you have a charged particle. So
Yeah, NEDA will not be available.
Okay.
Because in the other configuration. But
it's
I
for
prepare
0 degrees, right?
Yeah, for the 0. I prepare 2 backup slides.
NEDA is with Prisma and Agata, or
Yeah, but
You can
Prisma
use
is
as
not
well
very
Prisma or
sensitive
not?
to light ions, like in our case. So my ideal experiment is to run again beryllium-7 on lead-208 and to do something like what was done at Triumph with Tigris, because then you can separate inelastic scattering or those experiments that were performed also at Ganil by Navin. We might think to something like this. This is for our side, or for our community or our family. From the gamma collaboration, they might be interested in studying the isospin asymmetry between carbon 11 and boron 11, and this is the idea by Andrea Gottardo. So these are the first 2 ideas somehow.
Nice. Another question, well, it's more a comment. I remember I was working with Giovanna Benzoni in the mechanics for sugar. What about the new chamber that they have? They are planning for 0 degrees. Probably you can use the chamber in the present configuration, and it's bigger than the present one.
Yeah,
no?
but I'm afraid we have to use this one. And if you ask me about the
textures, I mean, it has more room for.
But it will be for the 0 degree, I guess, not for this one.
I think that it could work if you move Prisma a bit.
It's a bit heavy, yeah?
A bit. Thank you.
Okay.
Somebody else?
another question? Yes, Vasily?
Thank you, Marco, for a very nice presentation and also all the options of the facility now. I would like to ask for a comparison between the old system of PPACs and the new of MCPs. Comparison from the point of view, what is extremely better, what is worse?
So, first of all, the beam rate.
The mapping of the beam now, is it better? Or
Okay, I can tell you that when we ran the experiment with the people from Catania for, the Trojan experiment that I was describing in the previous talk, we removed the PPACs and we were able to run for 13 days continuously. Otherwise, every second day, almost, we have to replace one of the PPACs, especially when you have a very high secondary beam rate. So in this case, the advantage is that we are losing less energy because we just have 1 layer to cross and not 3 layers plus the gas. The counting rate that we can stand is larger. So I hope at least 5 × 10⁵ particles per second. We will see. And then we don't have gas leakage from the windows and all the problems that we had. The other problem is that we didn't know anything about microchannel plates until 1 year ago. So we are studying and learning, but that's the only way that you can do something new. Otherwise you always do the same thing, but you never improve yourself.
It's an exploratory phase.
Yeah. And then we have Sarah, and she's fully dedicated somehow to the microchannel plate, and that is, it was a big step forward for us.
I think it's better, no? Maybe you lose some efficiency, but you save a lot of time.
And also no gas circulation. It was a nightmare almost. Yeah?
And you still can produce this nice beryllium-7 beam, which is 99% pure, that you saw before. This I talked to Patrick. So these guys, yes, they use another reaction to produce beryllium-7 in order to be pure.
Which can be at higher energies.
Yeah, up to 42 MeV we went.
Okay. Okay.
Francesco? Oh.
No, it's a very small. So I remember that with a similar microchannel plate detector, same size, same delay line concept and so on, using a magnetic field, we were able to reach something like 0.7 millimeters resolution. But everything becomes a little bit more large.
Yeah. I can tell you just in 1 minute a funny story, because at the very, originally we put this chamber attached to the exit of the quadrupole. Then we have to move once because we bought some magnets from a company, but actually the magnetic field that we measure inside is not enough. So now we put some huge spires, and we have to move the scattering chamber once more in order to allow. And we still have to receive from the company the new iron brick to put inside in order to increase the magnetic field.
So you use a magnetic field in the
Yeah. Not enough, but I hope for July we should be able to put a stronger magnetic field.
Okay.
Okay.
Thank you.
Thank you very much.
We are still at home, and I call Luis Acosta from the Autonomous University of Mexico and from Spain with the title Recent Results for the Dynamics of Alloy Nuclei at Barrier Energies.
Well, I'm started with some advantage because many things were mentioned before by my colleagues. So, well, I'm now in some kind of hybrid shape, jumping between CSIC at Madrid and INFN in Mexico, that I was working there during the last 9 years. So I'm gonna show you, sort of results that we made during the last, it's now a lot of time, last more than 20 years. So let me start with this outlook. The developing of technology regarding beam production, charged particle detections, and data acquisition system is allowing to revisit some reactions involving weakly bound nuclei. And during the last 7 years, I'm speaking just of this short period about the experiments that we made in this short period. We developed a number of these experiments in different laboratories, mostly halo nuclei, impinging medium mass and heavy targets at energies that is usual at the vicinity of the Coulomb barrier, where you know that we can study this transition between Coulomb and nuclear potentials. And for several years, this analysis of these kinds of reaction has shown a degree of difference in the case of the elastic scattering compared with the stable similar nuclei, as many of my colleagues show before. But moreover, the reaction products are shown in particular cases preference to follow or not follow a different process. So I'm going to speak a little bit about that. And the global conclusion shows that not all the halos follow the same behavior when their dynamics are tested at these Coulomb energies. And I'm going to show a bit in this work some of these cases. Well, first of all, I'm gonna go to the past a bit. We made very successful experiments at Trion Laboratory. Between this one is in 2008 and 2009, and the other in 2011 to 2012, I think. We studied beryllium-11 and lithium-11 scattering and products. As you can see here, there is the case of elastic scattering. This is our array. We start to be some kind of pioneers using these kind of detectors, these silicon strip detectors, square ones, in a telescope shape. As you can see here, this is the typical spectrum where we can see the elastic. In Trion, you have a very clean beam. It's an iso beam, and then here the breakup. So it was possible in this experiment that was analyzed by Juan Pablo Fernández Garcia and Mario Cubero as PhD thesis, the breakup and the elastic in the case of lithium. We see that we have this strong absorption that was expected in this kind of halo nuclei. This is the case of beryllium-11. It's just shown by Marco before. This is a very, very nice spectrum that was, to put in coincidence, this is the powerful of the gamma ray. A good gamma ray as Tigris, which is the same case of Agatha, when you put in coincidence with a silicon array. No? The silicon array is here. We use detectors from University of Huelva and also from Madrid to make this experiment. And the good thing of this measurement is, for the first time, we put disentangle the inelastic scattering of beryllium-11. but also first the breakup, but also the inelastic scattering using this coincidence to separate this excitation state. So it was a very successful measurement, and it was published in PRL as well of the other, as was the situation in the case of lithium-11. So it was also the PhD thesis of Vicente Pesudo from CSIC in Madrid. This is the case that is different, and we continue studying, as was shown by Angel this morning or in the last session. Maybe this is one of the most complete and wide angular distribution that is in the literature regarding the helium-6 around the column barrier. It was a combination of two experiments. The first was around 2002, I think, and the second in 2005. The combination is this wide angular range data. So, and the calculation was the one definitive proof that we have this strong absorption most associated to this dipole polarizability. But in the case of the breakup, we have a different situation. In this case, the calculations are related to transfer to the continuum. It's a DWBA. So, as you can see here in this circle, we have data in the elastic scattering at these angles, but we have not data published in the case of forward angles. So there is a reason for that, and was shown a little bit by Angel this morning. We have many problems with the collimators inside, with materials inside, and helium-6 is it shows this problem we saw in more than 3 experiments, that you have to be very careful in the case that you use this kind of collimators. So we use some copper to protect the strips. We were young, and this collimator, so probably the beam was impinging in the collimator and producing all this frame scattering. This is helium-6 in the frame scattering, and this is alpha. And in this circle is more or less expected. This these alphas from helium-6, probably from direct breakup. In the last years, around 2022, I revisit this experiment that was my PhD thesis with the help of one student, Jacqueline Perez, and she made a bachelor thesis doing this test. We remake again the analysis. We try to find in a better way the best spectrum, and we could reduce to try to isolate this part of alphas in one of the telescopes. And as you can see here in the you're watching the it's not the mouse is not there, right? Where is the laser? I'm just using the mouse and also Marco, where is the laser? So as you can see on the right in the plot. It's this one, no? Yeah. I try, but it doesn't work. Maybe this. Now? Now. Now, yeah, okay. Good, it's better. So as you can see here, these 3 or 4 data are very close to what was the prediction of the CDCC calculation at that period. That is an image that just appeared in my thesis. We never dared to publish. So in that direction, we planned the experiment that was shown by Angel in the last session, where we use a very similar configuration, taking many hours planning how to avoid this problem with the frame scattering. It seems, as I saw a couple of hours ago, that we will see. It's a promising measurement. And well, this is part of one experiment that we developed at Notre Dame, as Angel showed, and it's very recent, as you can see. The other was in 2005, but the publication was, the last publication was 2011. And this is very recent. It was developed the last year with the help of Patrick and all the student teams and Italian guys in Notre Dame. This is the case more eccentric, we can say. This is helium-8. When we make this experiment, that was in 2010, we have the possibility to develop a very, very nice array that is called Gloria. You can see here, Gloria has a lot of advantage in the case of the position of the detectors. It can measure very well angles. It has a good proportion between forward detectors. One detector forward is mirror to the other, exactly the same in the back. And we have on top measuring like all the detectors are tangent to some kind of ball or balloon. As you can see here, the results are tremendously good. These dots, these black dots, are the helium-8. Probably is also one of the most complete measurements in the case of the angular distribution around the column barrier. The energy was exactly the same that we used in the case of helium-6. As you can see here, the curious thing is that, helium-8 is predicted as a skin nuclei, so it means that the separation energy is much more than the case of helium-6, but we will see that it doesn't care because the absorption is really strong. So many other processes are participating there. This is the paper related to the Gloria array, and these are the articles where we describe this kind of behavior of the elastic. No. He's thinking. Now, these are the results for the products. You can see here in the spectrum that we have these two bananas. This is the banana related to helium-6 as products, and this is the banana related to helium-4. As you can see here, there are some calculations, and it's not possible in some way to have a good description of this data. These are fits, and the calculation for one neutron stripping, sorry, are here. So we have the shape, but we have not even no closer to try to be close to the helium-6 in this case. It's the same thing in the case of 16 MeV below the barrier and the case of 22 MeV. So it's very difficult to have or say something about what is happening here because we have many body problem. So well, the data are there, and it's something that it's an open question. This is the more recent case. It was not the last experiment that we developed in case of the Halo nuclei, but the analysis is the more recent one because we took a lot of time to develop this analysis of the experiment. The experiment was carried out at 2017 at a high Isolde facility. So we produced this carbon-15, but the case of carbon-15 is, well, it is saying that it's a very good candidate to be a halo nuclei. So it shows a narrow momentum and also a big cross-section in the case of reaction. So the unique thing is that the separation energy is a bit bigger than the case, for instance, of helium-6. And for two neutrons, well, it's incredibly big. So the possibility is one neutron halo. In order to know what was happening, we made this proposal that was proposed by Ismael Martel and Olof Temlat to be developed by Isolde. We made this experiment, and we use again, after 7 years, Gloria. We mount this new chamber that is mounted there at Isolde, that is called SEC, this Gloria array. And this is more or less what they can produce. This is a cocktail beam. We have this nitrogen-15 that is impossible to separate, and carbon-15. So as you can see, we have this effect of channeling that is, in this case, is very clean. It's practically out of the carbon-15, but it happened. It is not the same in the other cases in all the strips. We have to make very, very, very precise analysis pixel by pixel to try to disentangle these two guys. And this is the different beams that they produce to give us some kind of calibration beams. We try first with the nitrogen 15, but by kinematics, it was so problematic. So then we try with the different guys. We use finally this carbon 12, and again it's blocked. A lot of information. Here is thinking. No? No. Ah, no. Wait for the program to respond. Sorry. No, here it say that it's fluxing. I made something strange, I don't know. It's a way for the program to respond. Better. Maybe there are a lot of things open. You see?
Yeah, maybe you can close it.
Close the program. Try again. Okay. Let me go till, yes, I think. We will see. Here. I was here. In my data of carbon. Here. You could see? Okay. Let me show the pointer. So this is, these are the final results that we found. As you can see, as in the case of helium-6, comparing here with carbon 12 reaction at the same energy, we practically lose all the colon rainbows. So we are very ensured that we can ensure that the behavior is very similar to the Halo 1, and it's a perfect candidate to be. To be one, in the case of calculations, you can see here, this is practically all the rainbow disappear here. In the case of carbon, finally we have to divide by sectors. For the reason we have these big hero bars, we have to divide by sectors and to integrate pixel by pixel to try to save all the pixels with good information. And was a tremendous work developed by Vicente Tabora, first by Javier Ovejas. Also, they are two students from Madrid. It would be probably the most important experiment or the principal experiment of the thesis of Vicente that is close to make the defense. As you can see here, this is the breakup that we found. And well, we have tremendous doubts about that because in this region, we are not totally sure that this is working good. The curious thing is here that it's more or less similar to what is happening in the case of helium-6. So, well, we are waiting for the second revision. We will see. In principle, but referees say that it's okay. So probably it will be published very soon. Then there are these two approximations are also very, very recent results. We made the first experiment also in high solde. That was 2018 and was a proposal of Alessia Di Pietro that we measured there in this year, also using Gloria. This, as you know, is solde, well, it's an isol beam, as its name. And this is 1.5 over the column barrier. And the other experiment, this was one good thing, and I have to mention because it was the beginning of a very nice collaboration that was, in my case, as Mexican, it was not my first time. Mexico during many years was collaborating with Notre Dame. But in some moment, it never stopped, but it started to be less. But now we try to start again, and was thanks to Athena and also to James Colata that we start again, and we know to my friend Patrick is here, this experiment. At this period, we have new array of detection at Mexico. And a good thing of these two experiments is that I have the opportunity to work in these both experiments. In the setup, I built Gloria and I built also this detector. So this is CIMAS, that is a Mexican detector we used for the first experiment. And this is the chamber that is there. The good thing of CIMAS is that all the pieces are printed in a 3D printer. So you can get one piece in half an hour, more or less. It's a record time. And this is Gloria, as you know, many know. It's a metal piece where all the detectors are around. Here is the results from the first experiment, in the case of boronate on zinc. And you can see how it separates the boronate. And in the case of twin salt, it's different. We have there a cocktail, but with a very good time filter, we can separate very well. So the results from boronate, in the case of Isolde, well, shows that we have, even at above the barrier, we have a behavior that is very comparable with a normal nuclei, a stable nuclei. As you can see in the comparison with beryllium-11, the other isotopes of boron, the other isotopes similar to boron, beryllium-11 and beryllium-9. In the case of breakup, well, it's curious. I try to compare these two results. And we have very similar cross-section in both cases. We just need this peak that is projected by the calculation of Antonio Moro in the first experiment. But we have to mention that we have in other order a different energy below the barrier. So, well, as usual, in this case, for this reason, it's very important to make the developing of new facilities. We have large uncertainties that, and we cannot say many times, we cannot say the last word, but this is important to develop more and more these beams. This is the last experiment. I will be talked a bit by, well, in some minutes by Konstantina. We're very happy because we could build this new array, ICIMAS, in these two telescopes, and then with 4 ones. That was the last experiment, 2022, there at Notre Dame, where we measured boron-8 and beryllium-7. And well, we have now one article accepted, probably last week, and we are also very happy. So, some conclusions about this. There are very recent results related to dynamics of weakly bound nuclei, and some from the last 20 years. In the case of 1 neutron, 2 neutron, 1 proton halo, and in the case of helium-8, 4 neutron skin. And we can say that while the elastic scattering is most of the cases show a well-identified behavior, strong absorption in the case of neutron halo, and a stable behavior, or more similar to stable behavior in the case of proton halo, the reaction products not always seems to come from the same process. We have elastic breakup, transfer, non-elastic breakup, several kind of processes can occur, as we can see in the case of helium-8. And the exotic production is every time improved, as well as the detection system. That is very important, also the technology, as mentioned Marco before, and the DAC, because DAC is a very important thing also. In some of the cases, very precise and well measurements have been reached, and it's very important to continue the study of weakly bound nuclei to understand number of reaction effects and considering their importance, as Angel mentioned before, in astrophysical process. So, not names, many of institutions and funds. Thank you very much. And sorry for the technical problems. Tell me.
Slide 9, maybe.
Sorry?
Slide 9. The result for helium-8.
Helium-8.
Yeah. You show the angular distributions of helium-6 and alpha.
Yep. Here or here? Here.
No, the slide page 9 maybe.
Ah, you see helium-8. This one.
Yeah. So what's the curve for the? What's the curve? The red curve and the black one They are the calculations or
that are fits. I mean, in this case, are fits, and the unique calculations are these ones. In this case, and these ones. The others are just fitting the data. There is nothing really physics there behind. Why? Because we are far to make a calculations considering that we have many processes. So this is a one neutron stripping, and we can see that it's just following the trend, and that's it. But I think it's a big complicated problem from the theoretical point of view, of course.
Okay. Okay. Another question is about carbon-15. Yeah. There's a figure you show the PID of carbon-15.
Sorry?
Particle identification for carbon-15.
Yeah.
But could you show me where is the carbon-14 is?
There are, well, should be here.
Yeah, where is carbon-14?
Should be here.
Sorry, I can't see your point.
Sorry. Wait, why you cannot see? This is a laser? This one. Okay. It's really few.
Yeah, okay.
So it's not possible. I mean, this is a strip that is a channel that is at very forward angles. So if you go straight in the increasing the angle, you start to see practically nothing. And this is a common thing in this case. So this is the breakup that we could see, and in this case we consider that it's not deserved to publish in this case and try to make a new measurement, in fact.
And now we have a talk by Vlasios Petousis from the Czech Technical University of Prague, which it seems that it does not fit in that session. And I asked, when I had that paper submitted, I asked George Suliotis where to put it. I have only a place in exotic and weakly bound. But he said he's going to talk about X17.
Why I don't
This is more exotic than all the exotic that we are going to have in that. Okay, so go on.
Yes, just I need your help. So to start, thank you everybody. Thanks the organizers, especially my former professor, Paco. I feel rather emotional to be here. 32 years since I started my career at that university, this university. And now that we are looking forward to the dinner, which comes very soon. But now let me introduce you to what we call it constraints of the X17 boson from compact objects observations. I know that many of you think, what is the X17? Okay, the X17 is a particle, elusive particle to the moment, which it appeared in the Debrecen in Hungary in 2016 from Attila Karzahokai, can say the name right, who was actually, what he did, he used a proton beam, impinging a lithium target, the lithium target excites to beryllium, and then produces this X17 particle, which actually the reconstruction of the mass of the electron-positron pairs gives you a mass of 16.9 something MeV. Since then, many people try to reproduce it again. We tried also in Prague with a 3 years, now goes to 4th year project to build our detector around the world from CERN to Australia. But no other indications that we can see it again. But this is one of the particles that we can assume that could exist inside neutron stars. Why not? And actually we wrote after COVID or during COVID times, during the lockdown, we wrote a nice paper which actually proposed a model that this particle can mediate the nuclear force in long distances using instantaneous notion. And then we said, okay, why not? And then we had to make some constraints of this particle using compact objects, okay? So my outline is as follows. we have the motivation. I will tell you what motivated us to do these things. I will go through the equations of states. I think a lot of the previous speakers already made a lot of introduction, of course, of the equations of states. And then in these equations of states, we use three different methods, three different models and theories to approach this issue. The first one is the RMF theory, okay, relativistic field theory. The second is the momentum-dependent interaction, the MDI model, at the macroscopic level. And the last one is the color-flavor locked model for quark stars. So I'm going through all of them to see mostly the conclusion remarks, and of course to thank you all with the collaborators. So our motivation. The motivation, as I said, was to investigate this hypothetical X17 boson neutron stars and quark stars and using various hadronic equations of states with some phenomenological or macroscopic origin. And the main idea behind of this is just to introduce some parameters that we can put constraints in this X17 existence inside the neutron star. So one of them is its coupling constant, which may have to the hadrons and quarks, and the other is something which someone can find also in condensed matter physics and also in high-dense environments. This is called the in-medium effect parameter. We call it regulator because we can play with this and regulate exactly the effective mass. I will show you a little bit later what I'm talking about. And of course, the main outcome of this analysis was just to see, to check causality, possible upper mass limits that the stars could give us, okay? Inside, of course, all the constraints from the speed of sound to the tidal deformability. And then, as I mentioned, tidal deformability is one of the key features that we use today, especially after this multi-messenger astronomy for gravitational waves, who check mostly the radius of the neutron stars. Mostly information comes from binary systems that we are merging phase. And then, a little bit about a few things. Continue the motivation, which is more a little bit technical now. I will start with this part that we call it weakly interactive light bosons. And I'm using this weakly interactive light boson because if we're talking about the small distances and a mediation between nuclei or even particles which could be dark matter, we need these small distances. We need some light particles, actually mediators of the force, as we say, the strong force, the weak force, electromagnetic force. We need some boson to mediate this force. And then theories developed in the realm that we call beyond standard model physics to introduce these particles which are really, really weakly coupled with the normal matter, the matter that we have today. I don't know if I can use my this is better. I can. The weakly coupled ordinary matter. So these particles is already studied that affect the equations of state, okay, change the equations of state, and of course, as an effect, this effectiveness changes, of course, the mass to the higher values. And then these ones also could provide some information about the strength, the coupling, which is important to the nucleus, to the normal matter, and of course to be able to estimate. Before we do this analysis, people try to estimate also the ratio between the coupling and this mass of the unknown weakly boson, which mediates the force in those small distances. And then it comes to your left part, this model, which call it non-Newtonian gravity model. Given this talk in a different audience, some people from the general relativity try to ask me what we modified, which is the energy tensor we modified, and how we go from this macroscopic classical space-time to this small distance. And actually, the answer is maybe is in your mind, the question is the same, but the answer, the very short answer is that we are just extending the inverse law, Newton law, with this small amount, which actually comes when the two particles are coming too close each other. Then there's a force in there, there's a potential between them, and this one, we know from high energy physics that can be introduced with the Yukawa potential, and of course you have a Yukawa coupling there. And of course this has a lot of terms, but this is very useful for us, because if you see, this is the normal Newtonian, and this is the Yukawa potential, and this is exactly some parameters, which the mostly important parameter is this lambda, which contains the 1 over mu, and here, this Ag, which actually contains the MB baryon squared, and of course the coupling. So most of the people at that time, because they don't have any information, especially before someone thinks that this X17 boson could be a weakly interactive light particle, all of the people just played with this ratio, estimating the ratio and only. And then we said with the collaborators and the people working together, if we think that this X17 could act as a light weakly interactive boson, then we have, because this is the mass of the intermediate boson, this one could act as already known parameter, and then we jump from two unknown parameters, which is only the ratio, to estimate the coupling. And this is actually one of the main key features behind this this job that we do. And after a lot of reading and learning things, even for non-Newtonian gravity, because also was not very well known to us. We have to study and to learn what the other people just doing, and this is a common process that everyone does. We started and said, okay, how we divide the problem, the problem, how we divide it? We divide it in that we know, okay, this using equations of state for RMF theory or MDI model. So we took this RMF theory, and let me introduce you here that this is the mass of the vector boson that we use, this X17. The rest, I'm not going to the details because it's quite technical, but I think most of the people here knows what is in there. But we did something else. We did it in a different way, that we are mixed it together with the omega. So instead of using only the mass of the vector boson, in order to make it more realistic, we take, okay, look, let's take this an effective mass, MV star, which actually has some percentage of mixing with this X17 compared to the M omega, this 1782 MeV. So we're just sharing an admixture between the omega and the X17, taking different percentages. Of course, we did the same thing with the MDI model, and using for the weakly interactive light particles, the baryons density, the pressure, and then the total equation of the total energy density is just the sum of the difference. It's just the sum, or the pressure is the sum between the baryonic and the bosonic interpretation. Then, since we do this admixture, we cannot do this admixture in all of the models, like the next one, which is the MDI model, who has a different, let's say, philosophy and formulation. And then for this case, we use something that we call the Bro-Rho scaling, that maybe know about this. Bro-Rho developed this theory mostly for the rho meson, which actually says very simple that the mass of the rho changes depending on the density and the environment where this meson is. So in this case, we used exactly the notion that the X17 particle can change whenever it's probably produced, appears, according to the surrounding environment and the density which experiences. Then you can have exactly these differences, and then we have an effective mass. Something which actually has an analogy in the RMF theory, using exactly this modification, this effective mass, exactly mixing, because mixing this with some percentage with the omega from the RMF field. And then we have two changes in the coupling. In this range, we can see it's between 10 to minus 3 to 10 to minus 2. And of course, this one corresponds to some ratio for this 17 MeV to be considered, that the G square over M, now boson square, it's between 3.5 to 10 to minus 3 to 1.7 G minus square. And of course, for people who want to follow, some can find the information here in the references. So if we continue, we did exactly, the last part is for the quark stars. So this here are the pressure and the energy density for the quark stars from the MIT back model. Then the energy for the boson is this one, and then the total energy density and the pressure comes from these two relations, which is actually the normal quark and this bosonic interaction. But what is important here, I would like to stress it here, it's this factor of 9, which makes, in the case of the quark stars, makes this contribution of the X17 boson, if it's there, much more pronounced. Of course, the different sets of parameters are going to go more, but last minute yesterday, I added something because I said, okay, not so many people know what is the color flavor locking model, which actually developed, as you can see here, in 1971 and later 1981, by Witten, which actually says that in a very high density, the mass of the strange quark is negligible, which actually is an idea that at the very, very end, all the matter consists only of up, as you can see here, up, down, and strange quarks. So it's kind of a pairing, kinds of the Cooper pairs that we have in superconductivity, but it's only in the level of the quarks, and this ones works very nicely. We have 3 colors, 3 flavors, and then these are locked somehow, but with the notion that this only exists only if you assume at that density, and probably this is correct because it's a first order transition, this one uses and be applicable when the mass of the strange quark goes to 0. But this is our technical details. More or less, what is the color flavor locked model, and the theory behind is already known. And then let's start with the results, which I think is the most important part. And then the first thing is the nuclear models from the RMF theory. Here on this table, you can see we use different equations of states. We play a little bit as a percentage increases the coupling in the row in the equations of state using the RMF model. And then for soft equations of states, this admixture between omega and the X17 was 20% of the X17, 80% of the omega. And then the effective mass which produced after this relation, which I showed you before, this is actually the row scaling for the RMF, produces exactly for pure Newton matter, produces this set of solving the Tolman equation, Volkov equations, produces these equations of states for a produces this mass radius relation for different equations of states, and you can see that more or less lies above 2, but 2 of them are very, very stiff. So these are the soft equations of states traversing the gravitational wave event observed by LIGO, this 1708-17. Here is this famous Hess remnant that we heard a lot of this about it today. And then there are 2 layers, two flyers here, which actually are the stiff equations of state. Then if we go to the checkpoint, which is the average standard informability with the versus of Q, where Q is the binary mass ratio, we see that these 2 here are above the upper limit, which predicted and set it by LIGO, and then these 2 exactly don't fit in the circle. We exclude it completely, but stiff equations of state going lower, and even the softer equations of state, which are going from up to down, from the top to bottom, then we go even deeper to the area which is allowed by LIGO. And then you can say higher, and we saw that if the coupling row that we are playing here, and also in the set of equations here, this 13 equations of set, we saw that the higher the coupling, the lower is the dimensional tight deformability, and it looks that this 20% admixture in the RMF model looks better than the 30% admixture, which means that this effective mass could be not so close to this one, but much closer to this one. And this is for the RMF. Of course, we did the same thing for beta equilibrium, okay, including neutrons, protons, and electrons. The behavior is exactly the same. Soft equations of state, stiff equations of state, masses effective are the same. More states now, more equations of states are softer, okay, but these 2 guys, these 2 bad guys exist even in the masses which is almost in area which is not so useful or also observed for neutron stars. But of course, these lines here, these horizontal colored lines, represents different already known pulsars that we have it as a reference guide, okay, in our models. Then we jumped to the other set in the microscopic origin, to the MDI model, which is the momentum dependence interaction. And you can see here, we used, of course, 3 reference representations for equations of states, where this L, which is the slope parameter of the nuclear symmetry energy, are settled without assuming the existence of the X17. So these are just pure without the X17 contribution. And then we started playing between the coupling G, and we saw that the variance between these two values, 0.11 and 0.22, and the representation in the MR diagram, it looks like these ones are more soft, okay, are going softer and going a little bit lower in the mass, in the radius regime. But what I have here with this an arrow and says X17, it says that this X17 contribution becomes, we saw that it becomes stronger and depends more stronger on the coupling than the parameter C. This is why we play mostly with the coupling, which is a very good thing, instead of this in medium effect parameter. So this is one of the results. And you can see here, if we go lower in L, we go from softer to stiffer, then we go from stiffer to softer, then we go that more deeper to the allowed area of the comes from LIGO. Then something which is not so easy somewhat to understand, so I try to bear with me, try to understand, to give you as much information as I can. Next step that we did, was that to make a plot which shows the maximum mass in respect with this medium regulator. Okay, but in this case we have a three-dimensional diagram, because one of the parameters that we are tuning and playing is just this was the G. And of course the tidal deformability was exactly the same, and we saw a tendency, which actually these peaks here denotes exactly the area where they have no violation of the causality, and all these areas that we have there, all these peaks shifted to the right for the X17, so the X17 becomes more pronounced, and then we violate causality. This is the notion of these diagrams. Then we did the same thing for the radius, and we just changed the levels. This is also a three-dimensional diagram, because every of this thickness here, it's the function of the parameter, this medium parameter C, and we saw that the effect goes and mostly appears between these two values of coupling and for the C maximum value. And of course the most important in this diagram here to your right, which shows exactly the combination between the G and the individual regulator. So we take here these two solar masses like a cutoff. We use this known, all well-known upper limit from LIGO, and then we're using three different configurations about the slope of the energy, and from all the parameters that we had, we can draw this valid region which looks like this curved triangle, and we say whatever lies in here, this one is exactly which preserves the correct parameters for the X17 existence between the G and the C. Of course, we do the same thing for the color flavor locked models. Of course, the equations of states are different. Here are transverse, and also this has remnant, the X17. And again, we used soft, medium, and stiff equations of state. So we're going from the stiff, medium, and soft. And you can see in this color flavor locked model, all of them are below the upper limit. And this is a very good idea. Doing exactly the same exercise, again, try to estimate the region between the C and the G. So as a function of G, which regulates now and plays different values for soft, medium, and stiff, we are able to estimate these triangles with the peaks denotes exactly of the constraints of the non-violation, and wherever we crossing the peak, this crossed lines here, we violate causality. And we try to estimate exactly how is the range of the C and the range of the G where the X17 becomes more profound. And of course, exactly the same exercise to estimate the phase space between the G and the C, and we're soft, medium, and stiff equations of state. We're able to predict maximum masses, 1.8 solar masses for the soft, 2.2 for the medium, and 2.4 solar masses for the stiff, which is not far away from something that can be, say, 3 or in the gap, in the mass gap or somewhere else. And of course, always here you can see this valid region, this funny triangle which goes less and bigger, and then we can estimate the correct combination between C and G in order to not violate any of the parameters. And then try to make things about the experiments. We found this one, and we say that, okay, if we see where the X17 stands in logarithm points of view, it stands somewhere there, though from experiments between low energy experiments between neutron and lead scattering, which is actually this experiment here, our measurements, our X17 lies here, and then we can go in a different masses and to make this extremely blue shaded band, which is an extrapolation to other masses. And of course, we know that we lie exactly here, and we're crossing one of the experimental in the Earth results. And then, stuck? No? Okay, and then that brings me to my conclusion remarks. Okay, what we did, we tried to pay attention between the couplings and the effectiveness of the in-medium regulator, because as we go into deeper densities and lower densities or higher densities to the center, then this one affects a lot the mass, the effective mass. We found that the stiffer is the equation of state, hadronic or quark, the more bigger is the effect and the properties of the X17 and these compact objects. Actually, is very strongly dependent from the coupling than the regulator. I mean, the coupling between the nucleus plays more important role than how deep we go, how dense we go, how modified the mass. Of course, is more profound in the quark stars, because this factor of 9, which I showed you in the beginning, which actually skyrockets all the results, and probably maybe we're able to estimate some kind of a new area of masses of these weakly interactive particles, and to give some information to the community about what this guy could be. And then I would like to finish with my collaborators, and with these ones, I think that we're on time. I want to thank you very much for everybody.
This is open to questions, and of course, Gatino is ready to ask something.
X17. So a couple of days ago, we had, a quite complicated meeting inside the Italian NTOF collaboration. Probably you know Carlo Gustavino.
The name only. Yeah,
so we are trying to measure, X17 by using neutron on helium-3. So it's a quite complicated experiment, okay, with a lot of...
This is why we tried 2016 until today, only the same group, Attila.
Yeah, exactly.
He did it 3 times.
That's the point. That's the point. So we are trying to understand also, actually, is there any other evidence with respect to the Attila experiment?
No.
So that's very important.
This is kind of as I use also the phrases that one of the previous speakers said. This looks a little bit suspicious, but
this is a crucial point.
It's a crucial.
Yeah, this is crucial since you have to justify this experiment in front of the CERN, INTC. So yeah, so that's a crucial point that we have to solve before continue.
Why it is so important to know if this particle exists, this boson? What is the motivation?
The motivation is that, according to our group thinking, is that, of course, it's something which is like nothing observed before. Okay, should be a vector, not a scalar, because violates parity, and then can mediate nuclear forces in longer distances. It's another, let's say, pi version, but in different environment. And we think that, personally believe that it's a nuclear effect, cannot be seen in high energy physics. So we need, as latest results from NA64 new a few days ago, announced that we're not so able to see something similar, or use it in connection with this dark photon, which is more or less excluded to be a dark photon. But it's a lot of discussion. It's a you mentioned, it's really controversial and elusive. And observed also in lithium, tritium, and carbon.
We need a confirmation. I mean, otherwise,
Cross-check, definitely.
Yeah. Okay, thanks.
Okay, do we have another question? Okay, let's thank again the speaker.
Thank you.
And now, the last talk, but not least, by our student Konstantina Palli, who is going to speak to us about the breakup of 8 boron zirconium-90 at the sub-barrier energy of 25.6 MeV, 26.5 MeV.
So good evening, everyone. Thank you for still being here. I know it has been a long day. Today I will talk about our work concerning the breakup of boron-8 and zirconium-90 at the sub-barrier energy of 26.5 MeV. So here's an overview of my presentation. I will start with the scientific motivation behind our work. I will continue with experimental details about the facility, beam production, and the detectors that we used. Then I will show you the breakup analysis and some preliminary results, and finish with some concluding remarks. The effect of coupling below the barrier, especially for weakly bound nuclei, has been a topic for interest for many years. There is a lot of work with weakly bound stable nuclei, and there's also work with radioactive nuclei that show a neutron halo structure, but not as many data for proton halo nuclei. This is one of the reasons that we chose to study boron-8. Boron-8 is a weakly bound radioactive nucleus. It is proton-rich with 5 protons and 3 neutrons and a possible proton halo structure. Possibly it has a beryllium core and a valence proton around it. It's also a nucleus that is important for astrophysics due to its involvement in the production of high-energy neutrinos in the sun. Generally, when we study reactions below the barrier, we have very small cross-sections. But with boron-8, we have the advantage of a measurable cross-section due to its very low breakup threshold of 137 keV. That leads to high probability for the breakup reactions to take place. Despite this expected large cross-section, weak coupling has been reported in the literature. Furthermore, there is a prediction for weakly bound nuclei. According to this, when we take into consideration the direct to total reaction cross-section ratio as a function of the energy, as can be seen in this plot, we observe the following. At energies near and above the barrier, this ratio seems similar for all targets and at around 20%. But as we move to energies below the barrier, the ratio shows a rapid increase, getting up to 70% for light targets, 80% for medium mass targets, and even up to 100% for heavy targets. So it would be interesting to see if boron-8 follows this systematic. The first measurement of our group, that is shown here, it's this point, is with boron-8 on lead 208 at 60% of the barrier. The measurement was taken at 2019 in Notre Dame. So here we see, even though the error is quite large, that the direct cross-section seems to be almost equal to the total reaction cross-section, and the ratio is around 1. Now we continue the study with a lighter target, zirconium-90. For this reaction, we expect that the dominant direct reaction channel would be breakup, and therefore by measuring the breakup cross-section, we will have measured the entirety of the direct cross-section. So in this work, we measured elastic scattering and breakup for boron-8 and zirconium at 26.5 MeV. This energy corresponds to around 0.9 of the Coulomb barrier. The elastic scattering results have been recently accepted for publication. We're expecting the paper to come out in a few days. The breakup I will present today. And alongside with this measurement, we also measured elastic scattering for beryllium-7 on zirconium at 5 sub-barrier energies. This has also been published in Physical Review C. The experiment took place at the Nuclear Science Laboratory of the University of Notre Dame using the TRISOL facility. Here we see the laboratory schematically. The 10 megavolt FN tandem accelerator is here. for the acceleration of the beam that then travels through the twin sol system here, that has now been upgraded with the addition of a third solenoid to trisol. The 8-boron beam was produced in flight using this two-proton transfer reaction. An helium-6 primary beam was accelerated at 37 MeV and impinged on an helium-3 gas target, producing boron-8 at 27.7 MeV, and as byproducts, beryllium-7 at 20.1 MeV and lithium-7 at 14.9 MeV. The products were then separated by time of flights and delta-E techniques. And for the beryllium-7 experiment, we used this reaction for the production of the beam. Here are some photographs of the trisol beam line. The primary gas target, that was helium-3 in our case, is here, for the production of the secondary beam and the byproducts that were then guided through the solenoids to the scattering chamber here at the end of the beam line. Some more photographs. The scattering chamber that we used here next to the electronics crate, and the detector system that also Luis Acosta showed earlier, inside the chamber around our target ladder. For our detectors, we used 4 delta-E telescopes consisted of a DSSD and a silicon pad detector. 3 of them were provided by the Autonomous National University of Mexico, and their DSSD had thickness of 20 micron. And the 4th one was provided by the University of Huelva, and the DSSD thickness was 15 micron. The pads were either 130 or 500 microns thick. The 4 telescopes, as can be seen in the figure here, were placed symmetrically around the target at a distance around 6 centimeters to cover an angular range of 20 to 60 degrees in the forward direction and 110 to 150 degrees in the backward direction. Now I will show some of the data. On the left, we see a delta-E versus E plot, where we can see the good separation between the elastic bands for boron-8 with pink and beryllium-7 with blue. This was very important for elastic scattering analysis. On the right, we can see a time of flight versus total energy plot. Again, the 2 nuclei are marked with the same colors. The time of flight was imposed between the first stage of the telescope and the RF poles of the buncher, and was necessary since our measurement was inclusive. Now I will describe a bit the breakup analysis. So far, we have analyzed the first few runs of our data, where we have good separation between the elastic beryllium-7 that's coming from the cocktail beam and the breakup products. This can be seen better in this plot. We have the time of flight on the x-axis and the total energy on the y-axis this time. This plot shows data from 3 successive strips, covering an angular range from 24 to 33 degrees. Boron here is on the top, and beryllium on the bottom in 4 successive cycles. So here, to obtain the breakup events, we take the appropriate time windows around the boron-8 elastic bands, and we can see the breakup events here. They're shown with the pink stars, clearly separated from the elastic beryllium-7. Now we'll show some preliminary results. On the left, we see the differential cross-sections, and on the right, the probability, the ratio of breakup events over boron-8 elastic events over the laboratory angle. The blue lines are CDCC calculations performed by Antonio Moro. From both of these plots, we see that the trend of the data is similar to the one of the calculation, but the experimental data seems to be higher at the more forward angles, and they approach the calculation as the angle increases. It's important to note here that the errors in these plots are quite large due to our very low statistics. So from this, we expect that the integrated breakup cross-section will be around 200 to 250 millibar, which is close to the value for the total reaction cross-section we obtained from the elastic scattering analysis. So now to summarize, complementary with our elastic scattering measurement for boron-8 and zirconium at the subbarrier energy of 26.5 MeV, we also measured breakup at the trisol facility in the University of Notre Dame. We performed the breakup analysis for the first part of our data, where we could separate well the elastic beryllium-7 and the breakup products. and presented some preliminary results for differential cross-section and probabilities compared with CDCC calculation. Generally, the experiment and the calculation are in a fair agreement within the errors, but with the calculation underestimating the cross-section. The breakup cross-section value that we get so far is quite large, close to the one of the total reaction cross-section, which is unlike what we expected originally from the phenomenological prediction, where we expected a direct to total ratio value around 0.8 for a medium mass nucleus like zirconium. However, due to the very large statistical errors, we cannot obtain absolute results just yet. As for our next steps, we're in the process of continuing the breakup analysis for the rest of our data to improve the statistics. The following runs have much better statistics, both the beam flux is higher and also there were more runs, so it will improve the statistics a lot. But there's not such good separation between the elastic beryllium 7 and breakup products, and so other techniques need to be employed, like the separation through the energy. With this, we will extract the breakup cross-section and the direct to total reaction cross-section ratio. Now I would like to acknowledge my funding, the Hellenic Foundation for Research and Innovation, for a PhD candidate scholarship for this work, and the Fulbright Greece Foundation for a 4-month visiting research student program that allowed me to stay in Notre Dame for 4 months. So thank you very much for your time. This is a picture that we took during the experiment. I think everyone in this picture is here today. Unfortunately, Luis had already left when we took it.
So this paper is now open to questions. Yes, Sherry?
Yeah.
The slide where you showed us where you identified the breakup events.
Mm-hmm.
We're seeing like 4 different beam bursts. Is that?
Here.
So those are like different beam bursts.
This is timing cycles.
Right. So I'm curious about the difference between one event, 4 events, and no events in subsequent time cycles. Is that a pattern that repeats? Is there any insight to that?
It's not always the same, since it is statistical, and generally we have very few events. Like for 3 strips, we have 1 breakup event over here. So it's not always consistent.
It's just statistical. Very few counts, yes, as you can see. And for certain angles. In other angles, we have different results.
Thanks, Konstantina, for this nice talk and for these results. The calculation is include just the elastic breakup, or you are
just elastic breakup.
You don't have any other process, because in general it happens. No? As you can see, you can include a non-elastic breakup.
We expect this will be almost negligible, but it will be a very low percentage of this.
Okay, no contribution. So okay.
We are below the barrier.
Mm-hmm. Yeah, I know.
This makes a difference, yes. Another question? Yes, Marco?
Okay, just a curiosity whether you look also at the backward detectors, whether you have any statistics.
For breakup, no, just on the forward ones.
Because you can see only 3 counts, 1 count, no count.
You can see from the errors that their statistic is not very good yet.
Okay, so let's thank again the speaker. And so this is the end of day 1 of this workshop, and now we can move slowly to the university restaurant. We can go walking. It's just 5 minutes walk.
Bring our stuff.
Yes, we should take with us the stuff. Mm-hmm.